Hi, welcome to today's video about dark energy and dark fluid. A nice deep field image of the James Webb Space Telescope from the galaxy cluster SMACS 072373. It's an exposure time of 12.5 hours. It's a cluster at time 4.6 billion years ago. We know since Hubble that we live in an expanding universe. The gravity is the weakest of the four fundamental forces. However, it has an infinite range. The mass of the universe is estimated to be at around 10 to the 53 kilograms. So you would expect a slowing of the expansion over time. But this is the opposite. We have an accelerating expansion. The faster expansion began 7.5 billion years ago here. And since then, dark energy is pulling the galaxies apart. Empty space that is created is not empty, it has its own energy. So if you have more space, you have more of the energy comes to existence. This is the energy distribution in the universe. 68% is dark energy. It causes the expansion at a large scale in the universe. 27% is dark matter. It's called dark matter because it has no interaction with light, but it interacts gravitationally. And the matter that we know, the ordinary matter, makes only 5%. This is another picture of the accelerated expansion of the universe. There's the lambda CDM model. CDM means cold dark matter. Cold means slowly moving dark matter. It describes the accelerated expansion of the universe. It fits nicely to the standard model, that's the Big Bang model. It can explain this cosmic background radiation, formation of the filaments of galaxies, expansion of the universe, and even the abundances of the elements hydrogen, helium, and lithium, and of the isotope deuterium. There's a nice artist's movie, a concept of the type I1a supernova. A white dwarf takes matter away from a nearby star. That makes this white dwarf unstable, and eventually it will explode. The light curve is shaped by the isotope nickel 656 with its half-life of 6 days. So type 1a supernovas are very interesting because they're called standard candles. So they should be the same in every galaxy. You can see multiple explosions here. And you can use these supernovas for determining the distances of faraway galaxies. A supernova is an important process which led to life because it distributes the generated elements into space that makes them available for future generations of stars. This is another example of a supernova type 1a, this SN 2014J in the galaxy Messier 82 in the year 2014. That's the supernova here. It is so bright that it outshines the entire galaxy. It can last for several weeks. And for a normal galaxy, there are about 1 to 3 supernovas per year. So if you observe enough galaxies, you can find supernovas. This is another image from the same galaxy, same supernova 2014J from Hubble Space Telescope. And this galaxy, Messier 82, is at a distance of 12 million light years. It is a starburst galaxy. And the reason is it is in interaction with its neighbor galaxy, Messier 81. The gravity of the second galaxy causes a compression of the gas in this galaxy, and this leads to star formation. This is a nice visualization of the cosmic microwave background radiation. In red, these are the slightly hotter areas, and in blue, the slightly cooler areas. This is the oldest detectable radiation that was emitted 380,000 years after the Big Bang. That's when the combination of protons and electrons to hydrogen atoms began. And since then, the wavelength has been stretched with the expansion of space. And one very fascinating thing about the cosmic microwave background radiation is a big area called cold spot. This is a bigger area with a slightly lower average temperature. And the first theory was that it could contain just fewer galaxies, that's why it's cooler. But this was not correct, and yet now there's another very interesting theory. It says maybe our universe collided with another universe, and that caused the cold spot. This animation of the Hubble's constant, that's the relative rate of expansion. This raisins and bread model. The raisins are the galaxies, the bread is the universe. So the Hubble's constant series predicts a number of 68 kilometers per second per megaparsec. 1 parsec is 3.26 light years. But the experimental data shows its number is 73 kilometers per second per megaparsec. Some experiments point even to 75 kilometers per second per megaparsec. And the reason for this difference is not clear. This diagram describes the future of the universe. The y-axis is the average distance between the galaxies. The x-axis is billions of years from now. We are now here. 13.8 billion years, that was when the Big Bang happened. And there are different scenarios. For example, there could be a continuous expansion, or there could be a big rip, or gravity could take over again, and this would lead to a big crunch. And these scenarios depend on the ratio of omega m to omega lambda. Omega m is the density of matter. Omega lambda is the dark energy density. And these are the scenarios for the future of the universe. If the big rip is a right theory, then it would happen in 60 billion years. There's another theory, that's the dark fluid theory. Dark energy and dark matter are unknown. And dark fluid theory says these are the two facets of a single fluid. That's the dark fluid, and that's the dark fluid theory. This is a nice picture of the dark energy spectroscopic instrument DESI from Arizona, USA. It will observe 40 million galaxies to find out more about dark matter and dark energy. This is a nice picture from the Dark Energy Survey. That's the isolated spiral galaxy NG3 1C98 at 65 million light years distance. Its size is 135,000 light years, so it's bigger than the Milky Way, and it contains over 100 billion stars. This is a nice picture of the galaxy cluster SDSS-J0150 plus 2725 from the Sloan Digital Sky Survey. This was another very successful survey over more than 20 years. The galaxy cluster is in the upper part of this image. It is at a distance of 3 billion light years. And the Sloan Digital Sky Survey has taken over 800,000 new spectra. This is an image of the Euclid Space Telescope. It was launched in July 2023. It will make measurements of the redshift of the galaxies. It will cover 1/3 of the sky, and it will bring us new information about the expansion and the structure of the universe. This is a nice picture of the star formation in the distant galaxies with the Spitzer Space Telescope, from the Spitzer Space Telescope. Recently there was new data from the James Webb Space Telescope, and according to this data there was a bursty star formation at the cosmic dawn that led to the abundance of the bright galaxies after the Big Bang. And this is a nice photography called Lights and Darkness of George Alexander Ishida Newman. It's a very nice picture. That was today's video about dark energy and dark fluid. You can check out the links to the scientific articles. Thank you for watching. Have a nice day. Bye-bye.